everyone, welcome to Learning at 11th Hour. In this video, I'm going to show you how we can analyze a given synchronous sequential circuit and arrive at something called the state diagram. Let me take you through the steps. We'll take up an example problem and see how this is done. Let us consider this example where two D flip-flops have been given and the inputs to the D flip-flop are as shown. So for the flip-flop A, the input comes from the XORed version of an external input X, and the other input of the XOR is going to be the B dash output of the B flip flop. And for flip flop B, the second one, the DB is going to come as an odd version of the external input X and A. That is the output of the first flip flop. We also have a final output here, which is the output of this entire sequential circuit, and that is the XOR version of the outputs of flip-flops A and B. So we now have to obtain the state diagram for this particular sequential circuit combination. So how do we do this? The first step is to obtain the equations for the inputs to each of the flip-flops. So let's begin. Step 1 is to obtain the inputs of flip-flops. So, considering flip-flop A, we have dA is going to be equal to X XORed with B dash, and dB is going to be equal to X ORed with A. Now, it is very important to note that in these both of these equations, the B dash and the A that we see, they are actually the outputs of these flip-flops, and they represent the instant n. Okay, so now that we've got the input equations for both the flip-flops, the next step is to obtain the equation for Z, the output, final output of these flip-flops. So step 2 is, what is Z? So Z is the XORed version of A and B, the present state of the output of both the flip-flops, right? So first two steps are done here. Next, we need to form the state table. The state table is going to be made up of the present state, the next state, and we are going to see how these states are transiting depending upon the external input X. So let's form the state table for this diagram. So here we see our state table with three basic columns. The first one is the present state, made up of A and Bn, the outputs of the two D flip-flops, flip-flop A and flip-flop B. The next state, made up of An plus 1 and Bn plus 1, but the outputs of both the D flip-flops is going to depend on the input X, and X could be either 0 or 1. So that's how the columns here are formed, and the output Z. The present state can be 0, 0, 0, 1, 1, 0, and 1, 1. These are the four possibilities that are there, considering both the present state of both flip flop A and flip flop B. So now we have to fill the rest of the columns with the help of the equations that we've just obtained. So in order to do that, we need to know the expression for the next state, that is Qn plus 1 for the flip-flop. So here we are actually using a D flip-flop. For the D flip-flop, the characteristic equation is Qn plus 1 is D. So in this case, if we are able to obtain the values for dA and dB for the different values of AN and BN, then it is as good as obtaining the values of AN plus 1 and BN plus 1 respectively. So let's go ahead and do that. So I'm directly going to fill AN plus 1 and BN plus 1 with the values that I get for dA and dB by substituting x, an, and bn. So in the first case, we have bn is 0. So here, this is bn bar, it's going to be 1. X in this column is 0. So 0 XORed with 1. So this is going to be 1. Let's complete this entire column. 0 XORed with 0 is going to be 0. Again, 0 XORed with 0 is 0. In this case, it's going to be here. And here we have 1 XORed with 0. So this is going to be 1. So next, let's move on to Bn plus 1. So for Bn plus 1, if we are able to obtain dB's value, we can fill up this column. Here, the value for x is 0, and it is ORed with an. So anything ORed with uh, 0 is going to be that value itself, right? So here we're going to get 0, 0, 1, and 1. Now let's move on to x is equal to 1. Now we have to obtain an plus 1 as 1 XORed with bn bar, right? So here we have bn bar being 1 in the first case. So 1 XORed with 1 is 0. 1 XORed with 0 is 1. 1 XORed with 1 is 0. 1 XORed with 0 is 1. Why do I say 0? Because I'm taking bn bar here. Now let's obtain bn plus 1 column. So again, we have to go for this equation. So bn plus 1 is actually x plus an. That is, this plus is the OR operator. So we need to find the OR version of 1 and an. So anything ORed with 1 is going to be 1. So we need not work very hard. We can directly fill up this column. Let's now find out the value for z. So we know that these are the values of an and bn. Z is XOR of the two, so 0, 1, 1, 0. So this becomes our state table. What we're going to do next is we are going to assign state names or state variables to these binary values, right? So I'm going to consider that 0, 0 is nothing but S naught. This is S1, S2, and S3. So in that case, if I put together these values, again I can obtain these next states in terms of the state variables. So 1, 0 here is nothing but S2. So I can replace this and write it as S2 and so on. So in that case, I would get something called as the state transition table, right? So when I do this, I will have the present state, the next state, and the output. So here again, I can obtain the present state as S0, S1, S2, and S3. Next state for x is equal to 0 and x is equal to 1, and z is the output. So z will be still the same, it will be 0, 1, 1, and 0 again. Whereas here we need to fill up uh, the next state based on the values, binary values over here. So let's do that. So here we have for 0, 0, we get for x is equal to 0, here we have 1, 0. 1, 0 is nothing but S2. Then 0, 0 is S0, 1, 1 is S3, and 0, 1 is S1, right? So I'm just going down like that. For x is equal to 1, 0, 1 is nothing but S1, 1, 1 is nothing but S3, 0, 1 again is S1, and 1, 1 is again S3. So in this manner, we've obtained the next state values, the next state and the present state in terms of the state variables. So this on a whole is called as the state transition table. Next, we are going to obtain the state diagram. So we have four states: S0, S1, S2, and S3. Now, there are two things that we need to consider. One is the change in X. The second is how does the output change with the change in state. So in this case, if we see, the output does not depend on the value X. So the external input has nothing to do with the output for any particular state. So if the present state is S naught, so for that particular state, the output is going to be 0. For S1, it is going to be 1. For S2, it is going to be 1. For S3, it is going to be 0. So we can embed the outputs within the state itself. So the denominator here that I am showing, that actually represents the Z, the value of Z. So this kind of state diagram where the output is embedded within the state and does not depend on the external input is called as a Moore machine or a Moore type state diagram. The other type is the mealy type, which we'll look at in another example, where the output would also be a function of some external input, and therefore it will change as the input changes. And in that case, it's not going to be fixed for one particular state. So it will not be embedded along with the state. It will be on the transition arrow where it will be represented in this manner. We'll have the input and the output. So this is how it would be represented in case of a mealy machine. But in this case, that's not what is happening. That's because uh, this is a Moore state machine. So here, let's see how the state transition is happening. In this case, we see the present state is S naught. When X is 0, the next state is S2. So I can go to S2 when X is 0, and it is going to S1 when X is 1. Similarly, from S1, it is going to make a transition to S0 for X is 0 and S3 for X is 1. So, for X is 0, S1 to S0. For X is 1, it is going to go from S1 to S3. Next, let's look at S2. So, from S2, it is going to go to S3 for X is equal to 0, and it is going to go to S1 for X is equal to 1. And S3. S3 is going to go to S1 for X is equal to 0, and it is going to remain in S3 for X is equal to 1. So this effectively is the state diagram for this particular flip-flop configuration, like this logic diagram that we had considered in the first place. So now if it is asked that for the sequence X is equal to say 1 1 0 0 1, what is the value of output going to be? So then we have to consider that the initial state is, say, assume initial state is S naught. So we have to begin from S naught. So for X is equal to 1, it is going to go to S1. So initial state, so let's fill up Z here, right? So when it was in S naught, the output would be 0. So when the input became 1, it is going to go to S1 and the output would be 1. Again, the input is 1. Now we are at the state S1. From this, again, when we receive 1 as our input, so this is where we'll go. So we'll go to S3 where the output is 0. From S3, if I get an input, say X is 0, then what happens? So for X is equal to 0, it is going to go back to state S1 where the output is 1. Now I'm at S1. Again, I receive the input 0. So when I receive the input 0, it is going to go to S0 where the output is 0. And from S0, suppose I receive the input X is equal to 1. So when I'm here, when I get X is 1, it is going to go back to S1. The output at S1 is going to be 1. So basically, if I connect an LED at the output of this configuration as shown over here, suppose I connect an LED over here. In that case, if I provide the input which I just showed, the LED would just alternately go on and off, right? So this is how we obtain the output sequence for a given input sequence for a sequential circuit. So that's all with this video. I hope the procedure for the analysis of synchronous sequential circuits is clear to you all. No matter what flip-flop it is, the basic steps are going to be the same. We need to obtain the input equation for the flip-flops, expression for the output of this configuration, and we need to obtain the characteristic equation for the particular flip-flops and relate it with the inputs, because we know the inputs in terms of all the connections and the external inputs that are there. So depending on that, our characteristic equations will also get modified. Once we get that, we can fill our state table and name the states and move on to state transition table. There is also a process where we have to be very careful with naming our states. Uh, that is called as state assignment, which I would be discussing in the upcoming videos. Thanks for watching.